Hello everyone and welcome to Climate Australia. I am your host, Lee Constable, and I'd like to start, as we always do, by acknowledging the traditional owners of the land on which I stand as I broadcast to you now. I am on the land of the Turrbal people north of Mianjin on the Kondamuka coast. So I am standing on their land, and I would like to acknowledge the elders past and present, as well as the ongoing relationship that Aboriginal and Torres Strait Islander people have in First Nations across what we now call Australia. And of course, acknowledge the relationship they have with the issues of climate change. And of course, with the uncertainty and risks that we're going to be talking about today. So also, whether you're watching on Facebook, YouTube, or here in the home of Climate Australia Simpatico TV, you are also joining us from Indigenous land. So I want to pay my respects to anyone who may be joining us who is a First Nations person today. Now, our topic of today is the unanswered questions. We're talking about the known unknowns of climate science and what that means in this critical decade when it comes to decision making. So my guest today is Professor Christian Jakob from the Centre of Excellence for Climate Extremes and also joining us from Monash University. Welcome to the show, Christian. It's great to have you.
Thank you very much, Lee, and welcome everybody, and thank you for having me on.
It's my pleasure. It's something we often talk about, known knowns, when we talk to climate scientists. What do we know? Why did you think it was time now to talk about the known unknowns?
Well, look, climate science has done a tremendous job over the last decades, really, to clarify big questions that society has for us, right? So we have now, just think about what we do. We have observations that go back hundreds of thousands of years from ice cores. We use observations that humans have made on the land. We use observations for the last few decades that satellites have made from outer space. We've built ourselves computer models based on sort of first principle of physics, and we use big supercomputers to calculate the climate and look at its future. And all these things tell us the same thing, right? They tell us the Earth is warming. They tell us that humans are responsible for that. And they tell us that if we keep emitting carbon dioxide into the atmosphere, the warming will continue. And given that information, governments have reacted, right? And perhaps the biggest reaction that we've seen is the Paris Agreement that pledges to keep that warming that we're anticipating to continue at a certain level. And that level is scientifically informed, and it sits at 1.5 to 2 degrees, right? And so I think climate science in the mitigation space, where it's about what should the global mean temperature be, has done a tremendous job. But here's the question to all the people around the world who are listening to this. When is the last time you planned a barbecue based on a forecast of global mean temperature? And that's what we're going to talk about today. Really, you don't, right? What you need is information where you live. And it turns out that providing that information out of climate science is actually one of the frontiers and one of the big challenges that we are facing for the next decade or so.
Yeah, so we think about these averages, and you're right, they are global averages. But I also wanted to just say that here in Australia, when it comes to warming, if we just look at our continent or our nation's warming, what are we already experiencing in terms of our averages before we go down into what we're missing in terms of local?
Well, we've seen Australia warm by more than 1 degree, right? And so we have certain. Well, we have more than observations though, right? We have the theoretical knowledge, we have the computer models that tell us that warming isn't a natural event. It's actually something to do with human activity. And temperature, we will come back to that in the later discussion perhaps as well. There are certain variables that are a bit easier for us to say something about, and temperature happens to be one of them, right? Because the laws that govern how temperature, especially over large areas, varies. That's much easier to sort of express in with our science, understand, have theories about, support those theories with observations and models, than it is, for instance, about learning how rainfall is going to change, even over large areas, it's quite much more difficult to say how rainfall is going to change. But rainfall is societally massively important for many, many, many of our activities.
Yeah, so when we come to thinking about what this means on the smaller scale, not just in terms of geographically, so what it means to get this sorts of information here in, for instance, Southeast Queensland, but then we're also looking at what it means across a shorter time frame. What does it mean to my barbecue tomorrow? That's the kind of example you gave. Are we not already there when it comes to broadcasting forecasting these things on our broadcasts we see?
Well, we are there if we want to forecast them for a week. So we have very good knowledge these days, and most people, as much as everybody complains about the weather forecast being wrong again, actually, if you look inside and take a scientific view of this, is absolutely not true. Weather forecasts have improved tremendously over the last few decades. And so if you're asking, can I have a barbecue next Sunday? Or is there going to be, perhaps more importantly than barbecues, is there going to be a heat wave event in your area next Sunday? We can give you very good information about that. But that's not the question we are about. And this is the fascination where the science now needs to combine this sort of weather knowledge, if you want to call it that, with the longer term variations in climate. The question is, how is the slowly warming climate going to affect heat waves in your area? Mm-hmm. That's the question. And so we want to predict not a particular heat wave in 2050 and in 2080, but we want to give you information. Will there be more heat waves? Will they be stronger? Will they be longer? For heat waves, we in fact have some skill in doing that as well, because it's related to temperature. But if you want to know, is there more flooding rains coming? Will a typical summer in 2050, what will that look like where you live? A typical winter in 2050, what will that look like? That's a really important question to answer. And it's really, really hard. And it's really, really hard because it involves movement, circulations of the atmosphere and the ocean that play off each other as well. And as the climate changes, these circulations change. And predicting that actually turns out to be quite challenging at this point in time.
And what sort of support do climate scientists currently have to actually answer these questions? Are there enough people doing this type of research? Is there enough of this research valued around the world?
So there's several aspects to this. If we're just thinking about looking into the future, right? The main tool we have to do that are these computer models that I was talking about. And what they are representations of the laws of physics. So some of you might remember from high school, Newton's second law. So that's Newton's second law is actually in there. But the way they are built, we then need to divide the Earth up into little boxes. And mathematics says make the boxes really, really small if you can. But the computers that we have available to look into the future with these models don't allow us to make the boxes as small as we would like them to make. So a typical climate model divides the Earth up into areas of, say, boxes of 100 by 100 kilometers in the horizontal and maybe 500 meters or so in the vertical. So we end up with this onion layers and vertical boxes all over the world, right?
Yeah.
The problem is the weather that we are interested in is often much smaller than those boxes. Think of thunderstorms, right? A thunderstorm is a few kilometers across. In a box of 100 kilometers, how do you deal with thunderstorms? The computer model itself knows nothing about thunderstorms, so we put them back in with what I call little models in the big model. They're called, the formal term is parametrizations, and those then express the action of thunderstorms within that box. And so that's an additional approximation that we would like not to make. Right. And because it's an additional approximation, it increases the uncertainty as to what we can say, how the climate is going to change locally. And there's the other issue that is really cool about this problem is that there's so many scales involved, right? We have the global mean climate, but we know that varies. Every one of us knows that the climate's varying because most regions we live in, not so much in the tropical regions, experience a very distinct summer season and a very distinct winter season, and that's because the climate varies, and that's forced by the orbit of the Earth around the sun. That's all pretty easy to understand. But the climate also varies because things in it interact with each other. So a very famous climate variability feature that everybody's heard about is El Nino Southern Oscillation, El Ninos, La Ninas, we've heard about them. That's produced entirely by the ocean and atmosphere playing off each other. And so that makes the climate vary interannually, every few years. And then the weather varies every week. And all these things interact with each other. And all that needs to be in our computer models. So what's the issue? The issue is that we really need to push the boundaries of technology because we need the computers. We need to really push the boundaries of science because we need to make these models represent what is the weather. So if we want to do thunderstorms, our boxes need to be 1 kilometer wide, not 100 kilometers wide.
Otherwise, you potentially miss something, just like, you know, trying to use, I often use a microscope analogy for these things, just like trying to use, you know, some binoculars instead to look at something as small as a grain.
Yeah, that's it. So the issue is that we want to know about the thunderstorms, but it's even more complex than that because the little thunderstorms do affect climate at very large scales. So, you know, if you have a bunch of thunderstorms in a 100 by 100 kilometer area, can make a big difference to how exactly an El Nino will play out. So if you get it wrong, you get how an El Nino will play out wrong, and that has much larger consequences. So really, the challenge here is to build models of the climate that have these weather scales built in rather than have to rely on these little models in the big models. And that's a scientific challenge. There's a scientific challenge also in understanding how does an El Nino interact with the rainfall systems over Australia. So we know that La Ninas on average tend to be wetter than usual. El Nino for Eastern Australia anyway seems to indicates drier. But how exactly that works, how exactly the weather changes as El Nino and La Nina occur is not as well known, and how the interactions between those two function. We don't understand that completely, right? We know statistically they are related to each other, but what the mechanisms are that build this relationship is not entirely clear. And our models are not quite there yet to help us understand that. So we really need these smaller boxes is the message, right?
Yeah. And I guess the answer to the models aren't there or the tech's not there is let's invest. Let's see what else we can do to make this, just accelerate being able to answer these questions. But I just wanted to turn your attention though to what are the implications if we don't know these things, and what implications even are we already seeing from not knowing these things?
Yeah, look, I'm not an expert in climate impacts, but I think I don't need to be to see some obvious implications, right? So here's an interesting factoid for people who live in Australia. For most of the eastern half of Australia, half the annual rain falls in 2 weeks, maybe 3, somewhere between 2 and 3 weeks. So that means a few weather events can change dramatically what the annual average rainfall. Now, we care about the annual average rainfall because it determines the viability of agriculture. The absence of rain brings drought to Australia, which is a big topic here. People will know, and not just here in the US, they suffer big drought. So the absence of rain. And we're talking about a few weeks, right? A few weeks of rain make a big difference. Getting those, that makes a big difference. But if you're a farmer, if all that rain fell in 3 days and flooded your fields, that would not exactly be a good outcome. So it's not good enough for me to know whether I get a lot of rain this year or not a lot of rain. That's the first order thing I'd like to know. But I also need to know what's the sequence of that rain. When is it going to fall? Is there going to be a week of light rain just at the right time when I'm planting? Or is there going to be a deluge right when I want to bring my harvest in? And we will never predict this for 2050 for a summer in 2050 now, but we can predict what the likelihoods are and how this is going to change on average. So to me, it's really about the question that we need to answer. What's a typical summer in 2050, a typical winter in 2050, 2080?
And not just what are the risks, but how likely are we to experience them, and for how long and to what extent?
Yes, and So it's clear to me that, heat waves is another example. Heat waves are relatively short events, but they kill a lot of people. So we really need to get a good understanding of what's going to happen. Are the heat waves going to be longer? Are they going to be more intense? Is the nighttime temperature or the daytime temperature going to change more? Without knowing that, planning a response, and climate adaptation is perhaps the big field that will benefit the most from us knowing these things in more detail. And in fact, I would argue we need to know them in some detail for us to be able to make good decisions about how do we want to adapt, what are our systems with which we have available to us to respond to these changes, how should we build them, what should be in them. So I think it's really important to not just know what's going to be the average change over a year, but what are the sequences? Will we get larger extreme rainfall events? Do we therefore need to prepare ourselves for that?
And I suppose as you learn more through being able to do more research into these things, your ability to refine becomes greater, so that the ideal would be, we know that next year the January to May period will be most likely characterized in this way. And then the farmer can say, okay, well, maybe I'll hold off in planting that until I see this, or something like that in terms of decision making.
That's actually an interesting point. So there's several time scales over which we make predictions, right? We already talked about weather prediction, and the reason this works is that if we know what the atmosphere pretty much by itself is like today, and we know this from observations, and we combine those observations with our model information, we can make a good forecast of the next week or so of how the atmosphere will evolve, right? Great. If we know what the ocean is like today and the atmosphere is like today, we can and we do actually make predictions for the next season or two ahead, 3 to 6 months ahead, even 9 months ahead. So those two boundaries we've cracked, right? So that now we also are able to make large scale global average, continental average estimates. And remember, those are not predictions. It's very important to keep that in mind for everybody who's listening. To actually look into 2100 or 2080, we need to assume how humans will behave. And that's done by creating scenarios. You will all have heard the business as usual, the scenario, the strong action scenario.
And I think this also relates to what people would have heard this year when it comes to epidemiologists. They are also modelers, just like different modeling, but again, they have to have assumptions, and it's not a prediction or a crystal ball. They just go, if everyone behaves in X, Y, Z way, we'll see numbers around this. If everyone behaves in this way, numbers around that.
Yeah, the models are quite different models, and they're built quite differently, but that's not the point. The point is that in a world where you cannot rely on the current status alone to say what the future will hold, but you need to know something more. So for example, here we need to know what are the fossil fuel emissions going to be like, and we don't know what they're going to be like. But therefore, we can say, well, what if we carried on as normal? What if we took dramatic action? What if we brought them to zero by a certain time? How would the Earth react, right? And that's quite different from making a weather forecast where we say, I know what the weather is going to be like today. Yeah. Therefore, I have the ability to use my model to predict what it might be like in 3, 5, 7, or 10 days. Right?
And the potential for emissions to go up or down over the next month is very different than the scale you'd be looking at over 20, 50
That's
years.
Absolutely right. So the weather forecast doesn't change the carbon dioxide concentration in the atmosphere. It doesn't need to, because it only goes for a week. To look at what the world might look like in 2080, everything depends on what the carbon dioxide emissions are doing between now and then, right? The answer depends very strongly on that. As we said, we know that carbon dioxide emissions are directly related to the global mean temperature change of the Earth, and there's no unknown about this anymore. The exact range has some uncertainty to it, but there is no unknown there. The unknown is how's that going to play out locally, where people have, and a lot of decisions that have to be made about how we're going to respond to climate change are local decisions, right?
Yeah.
It's all the way down to local councils
Yeah.
trying to think about climate adaptation, storm surges, depending where you are.
Small businesses.
Small businesses.
Yeah, it comes into financial forecasting and investing and insurance.
Yeah, so I think the key element here is the key unknown is that this translation of the global change about which we are certain into local change is a scientific frontier, and it's often underestimated how big a frontier it actually is, and that it does require quite a lot more work, improved technology, improved ability to model, and improved ability to take the data that we have about this and turn it into information, right? Scientists, we produce a lot of data, but people don't want data. People want information, and that's not the same thing. People think, if we produce a lot of data, people have information. So there's another big step to be made, is how do we take that data that we are getting from our models and help people produce information for people on which they can make decisions. So that's not my area. I don't work there. I'm working on this first frontier, is to produce the underpinning for that information, which is, trying to estimate how is the weather going to change. The big question that we dance around it all the time and haven't asked it is, how is the weather going to change with climate change? And we need to know that to make good adaptation decisions.
Yeah, absolutely. And it's important for people who are in the business of translating data into meaningful information, into policy and action, and every step of that way to know about your end of things. Because, do you see that as a reason for doing a podcast like this or a live stream like this?
Well, for me, it's just I want people to be aware of this, that there has been a big impression that climate science is a solved problem, right? And for certain aspects of climate science, that is true. And as I said at the beginning of the podcast, the impact that climate science has had is tremendous, and our knowledge on large scales, global, continental scales, has directly translated into policy, right? And it has because it's reliable, there's a good understanding, and we would like to have the same effect locally. It would be wonderful if climate science could play the same role it has played globally, leading up to the Paris Agreement for mitigation, to play the same role locally for adaptation. I think that's the goal. That's a goal every climate scientist should have. And that requires investment in the science, and not the attitude that, because we know what the global answer is, we're done. We can now focus on decision-making alone. So it has to be a handshake, but there is fundamental science. There are fundamental unknowns that we have to address, like in any other science, right?
Yeah.
And they are also the things scientists get out of bed for, right? It's these unknowns. It's not the things we already know.
Absolutely.
I get out of bed because there's lots of things I don't know.
Yeah, and when you can see such a critical link between what you don't know and what you need to find out, and what this could mean for people's lives and livelihoods, no wonder that gets you out of bed every day. That's
Absolutely.
A big motivator. I just want to shout out to everyone who's been watching the live stream here in Simpatico TV and in Facebook and YouTube. Andrew Watkins on Facebook earlier was adding to your comments about the things we don't know. Indian Ocean Dipole, he said as well.
Yep.
And Sarah on the Simpatico TV chat has shared what Andrew shared, which is the BOM Bureau of Meteorology, for those not in Australia, seasonal outlooks for the months ahead at bom.gov.au, BOM. And also Peter on Facebook said, those willing to work hard for seasonal outlook and customize it, this may be helpful. And Peter actually shared a link there to climate.copernicus.eu data set on seasonal and monthly levels.
So there's another fantastic output of weather and climate science jointly here, I would say, that we apply these computer models, not just to look a week ahead, but we look a few months ahead. And we can do it because we don't just look at the atmosphere. And that's another fascinating thing about climate science, of course. It's not just people thinking about the atmosphere. There's the information to be able to make a 3 to 6 months forecast resides in the ocean, not in the atmosphere, right? And so it's oceans. It also, to some degree, resides in the land. What is the current state of the land? Is it very dry? Is it very wet when we begin and look ahead for a few months? So we have this interactivity. Ice plays a massive role for climate, right? We have these big ice sheets, Antarctica and Greenland. We have ice floating on the ocean. That affects how weather systems evolve as well. And so it's very interdisciplinary as well as being, so this answer to how the weather is going to change doesn't just depend on what the atmosphere is going to do and understanding the atmosphere. It depends on understanding the ocean, the land, the ice, and how they all interact with each other.
And the more you're talking, the more I'm thinking of example after example where I can see why that's an issue, because, while we're talking about global warming is the term that was used and is still used a lot, obviously that's an average. And in some places that means a huge snowfall where they don't normally get snow as much or for longer. And then that can lead to more reflection potentially, while down here we're having heat waves. And I think often we forget because, I find, this is my view, I'm sure lots of others in the Southern Hemisphere would feel like the media and discussion around things is very Northern Hemisphere focused, but we also have interaction between another half the planet who's having a totally different, season, and those seasons are shifting at the same time in different directions.
This brings us back to investment, right? Being a bit parochial here, we are in Australia, you and I are. If the weather in Australia is very different from the weather in Europe, right? So if we want to contribute to these solutions at local level, we need to understand not the weather in Europe, we need to understand the one in Australia and how it interacts. And who's going to be likely wanting to understand that? It's Australians, right? So I think, and this is true for every place in the world. So some of that investment into the science, this is both a curse and an opportunity, but there's an opportunity to invest in science locally, wherever you are, in Africa, in South America, in this Indian subcontinent, it doesn't matter, because some of the things you need to study to understand this interaction between the vessels. So the climate is global, so we need to understand it at that scale, and we are pretty good at doing that, and we have a large international community that works together to do that very well. But the impacts are local, right? And so the change in the weather that we are going to experience as the climate is changing is a local issue. And so therefore there needs to be investment in science all over the world that looks at these local aspects.
And also there needs to be some equity in that, because we have to recognize that Pacific Islands, for instance, Caribbean nations, the Torres Strait, when we're talking about here in Australia, for instance, which is part of Australia that doesn't get enough attention, they have a great need for local information, for information that's relevant to island nations, but don't always have the same funding to research these models.
So that's where international collaboration comes in as well. And I want to give a shout out to a big project I've started, and we're just starting up as part of the World Climate Research Program called Digital Earth. And the idea of Digital Earth is really to take the new technology, the new gains we've made in artificial intelligence, the gains we've made in climate science, the gains we've made in information science, and put them all together to provide, let's call it an information system about climate that is open, publicly accessible by anybody, shared, the technology, interoperable, so whatever gets developed in this part of the world can be used in another part of the world, and gives access to the world to really, really good climate information. Now that's a decadal project. It's not something we're going to do next week. But people are thinking about this, and it is going to be global. So the information it's going to produce will be for everybody, right? So, and will cover, and I think this is where we can make a tremendous contribution to, you mentioned Pacific Islands, but other nations that don't have the capability to build these sophisticated systems themselves by giving them access to their results. Right? And that's the plan. That's the plan.
Yeah, and I think also Peter on Facebook is saying international insurers from the Northern Hemisphere probably care about Southern Hemisphere weather too, especially now post-Black Summer. And I think that makes me think of the conversations I've been having with more people, especially in, for instance, California, where, you know, it's very easy to look at the fires that were happening from late last year all the way up until late February in some places and say, wow, how terrible for Australia. But if you don't also think, is that coming to us our next summer? And what can we learn from them? And what information can we share from what we're experiencing and learning in for instance, California or wherever else it might be? Yeah, it makes sense.
Yes,
what someone's experiencing and finding out is relevant as long as, you know, you have that local context like you talked about.
And guess what? It's very well known that these big fire events are spurred on by certain weather events, right? So again, if we want to have an answer to what's going to happen to bushfires under a warmer climate, we know the Earth is going to warm, and we know that's going to have an effect, right? So that part is easy. But it could be so much worse than just the warming effect, or it could be slightly less worse than just the warming effect, because the weather systems that drive bushfire behavior may change in a certain way. And we need to know. We need to know. We need to know, is it so much worse than we thought? Or is it going to be not quite as bad as we think, just from thinking about temperature?
Yeah.
This is really, really important stuff.
And people use your research as a climate modeler to underpin their research questions and answers in public health, in, you know, bushfire management, in public policy, even in the urban landscape or in the rural landscape. So yeah, it really does filter down. I just want to, there's a few good questions coming in actually, I can see. We are going to have to call it a day for this recorded segment, but what I think we should do is we'll roll the credits at the end of this, and then we'll be hanging out here if anyone who's watching on YouTube, on Facebook, or here in Simpatico still has a question or wants to ask a few more questions. But thank you so much, Christian. It seems to sum up that it's good for us to talk about these known unknowns, because while it's great for us to celebrate what we do know and what has been achieved by climate science, if we don't keep our eye on what we don't know, then we won't be able to better inform what we're investing our time and tech and development and research and question asking and answering into in this critical decade for action. So thank you so much for coming along and telling us about that.
No, thank you, Lee. It's been wonderful to have the opportunity to talk to you.
Thanks very much for joining us, everyone, and we'll be right back after this. You've been watching Climate Australia with Lee Constable and my guest, Professor Christian Jakob from ARC Centre of Excellence for Climate Extremes and Monash University. Thanks.